Hello. Hello and welcome to this last read-through of permutation and combination. In this video, we will finish the remaining part of theory. So if you don't like to listen to someone else reading, then you can skip the video. And if you don't want to read yourself and listen to what I'm reading, then please watch. So there will not be much explanation because everything is written. So can very well go ahead and read. So without further ado, let's get started. And make sure that you have pen and paper so that you can write down the theorems. So we start with the inclusion-exclusion principle, or PI, principle of inclusion-exclusion. So we have seen examples of subtraction principle. Inclusion-exclusion principle is an extension of subtraction principle. In this type of problems, it is easier to make an indirect, it should be direct count of objects in a set rather than to count the objects directly. There is a huge typing mistake here. Consider following example. So the example says count the permutations I1, I2 through In of which 1, 2 through n, in which 1 is not in the first position, that is I1 not equal to 1. So the number of permutations 1, 2 through n with 1 in first position is the same as the number n minus 1 factorial of permutations of 2, 3 through n. So in n minus 1 factorial, 1 will be at its proper position. Since the total number of permutation is n factorial, required number of permutation is n factorial minus n minus 1 factorial. The number of objects of the set S that have none of the properties P1, P2 through Pn is given by the alternating expression. Size of A1 complement intersection A2 complement intersection through Am complement is given by size of S minus sigma size of Ai plus sigma size of intersection of Ai and Aj minus sigma size of intersection of Ai, Aj and Ak, and so on, where the first sum is over one subsets of I of 1 through m, the second sum is over two subsets Ij of 1 through n, and third is third subset, and so on. The subtraction principle is the simplest instance of inclusion-exclusion principle. As a first generalization of the subtraction principle, let S be a finite set of objects. Let P1 and P2 be two properties that each objects in S may or may not possess. This should be object. We wish to count the, give me a second. So we wish to count the number of objects in S that have neither the properties of P1 and P2. Extending the subtracting principle, we can do this by including all of the objects of S in our count. Then excluding all objects that have property P1 and excluding all objects that have property P2, and then noting that we have excluded objects having both properties twice. Readmitting all such objects once. Let A1 be the subset of objects of S that have property A1, and let A2 be the subset that have property P1. Then A1 complement consists of those which do not have property P1, and similarly A2 complement consists of those which do not have property P2. The objects of set A1 complement intersection A2 complement are those that have neither property P1 nor property P2. This should be P2. Thus we have size of A1 complement intersection size of A2 complement is equal to size of S minus size of A1 minus size of A2 plus size of intersection of A1 and A2. This comes straight from the set theory. Okay. We have similar relationship in S theory. To further prove this, we argue as follows. Consider an object S which has neither the property P1 nor the property P2. In this case, the contribution toward the count by this object would be 1 minus 0 plus 0 is equal to 1. Next, we consider if the property has property P2, then its contribution is 1 minus 0 plus 0 is equal to 0. And so on, we do it for P1. For the last property, when X has both properties, contribution would be 0. As it is obvious, any object will fall in either of these four possibilities, and total contribution is 1 only, which it has when it has neither of the properties. The inclusion-exclusion principle stated above is generalization of this two-property example. We will now establish the validity of the general case. First, consider object X with none of the properties. Its contribution to the right side would be 1. Since it is in S but in none of the other sets. Now consider an object Y which has exactly n greater than 1 of the properties. The contribution of Y to the size of S is equal to 1, that is MC0. Its contribution to summation of size of AI is n, that is MC1. Since it has exactly n of the properties, and so it is a member of exactly n of the sets out of A1, A2, through an. Similarly, the contribution of Y to summation of size of AI intersection AJ is MC2. Since we may select, there is a space missing here, that's wrong place. Since we may select a pair of the properties Y has in MC2 ways, following similarly, the net contribution would be MC0 minus MC1 plus MC2 through minus 1 to the power n MCn. And MCk is equal to 0 if k greater than n. The last expression is 0 from binomial theorem. Following similarly, we prove the inclusion-exclusion principle. So we have the number of objects S which have at least one of the properties P1, P2 through Pn is given by size of A1 union A2 union through Am is equal to size of summation of size of AI minus summation of size of AI intersection AJ and so on. The set A1 union A2 union through AM consists, there are lots of type mistakes. Okay. Of all those objects in S which possess at least one of the properties. Also, A1 union A2 union through AM is equal to S minus A1 union A2 through M complement. Then from De Morgan's law, we have this relationship. So following result from the previous definition, we have the required equality. Now we consider a special case of pi for any set A having n greater than 2 elements, A1 plus A2 plus through n. There is a pipe missing here at the end. So there should be a pipe here or bar. Will be equal to summation I is equal to 0 to n size of AI minus I less than j summation of AI aj summation of I j less than k AI aj aj. There should be pipes here. There should be pipes. There are lots of typing mistakes. In some problems, we deal with properties A1, A2 through n and numerical values associated with properties n A1 and A2 through n an and so on. We have n A1 is equal to n A2 is equal to n n, and then we have the two subsets and then three subsets and so on. Let NR denote the common properties of A1, A2 through n when taken R at a time, and 0 is the value of n A1 prime, A2 prime through an prime, where AI prime is the complementary property of AI and n is the value of the collection of 0 property or at least one property. Then we can write pi in the form n0 is equal to n minus nc1, n1, nc2, n of 2, nc3, n of 3, and so on. Now we consider derangements. Consider following problems. At a party, 14 gentlemen check their overcoats. In how many ways can their overcoats be returned so that no gentleman gets their own overcoat? In a cricket team, there are 11 players who bat in certain order. In how many ways those can bat so that no player bats at their predetermined positions? This type of problem fall in category of following general problem. Given an n element set S in which each element has a specified position, we have to find the number of permutations of S in which no element is in its specified position. This can be exemplified by a set 1 through n in which location of each integer is that specified by its position in the sequence 1 through n. Derangement is a permutation of I1, I2, I3 through In of 1, 2 through n such that there is another type of mistake, okay? Such that I1, this should be I1, is not equal to 1, I2 is not equal to 2, and In is not equal to n. Derangement of such an n element set is considered is denoted by dn for n greater than or equal to 1. Dn is equal to n factorial into 1 minus 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial through 1 minus 1 to the power n 1 by n factorial. Let T be the set of all n factorial permutations of x. For j is equal to 1 to through n, let Pj be the property that in a permutation j is in its proper position. Let Aj denote the set of permutations with property Pj. Thus, Dn will be equal to size of A1 complement intersection A2 complement through n complement. The permutations in A1 are that of the form 1 I2 through In, where I1, I2, In is a permutation of 2 through n. So 1 is at its proper location. Thus, size of A1 is n minus 1 factorial. We can write the general form as factorial Aj is equal to n minus 1 factorial. For Aj intersection Ak, two elements have to be in proper position. So intersection of Aj and Ak are n minus 2 factorial. For k integers, it would be n minus k factorial. Since there are n ck subsets of T, applying the inclusion exclusion principle, we obtain Dn is equal to n factorial minus nc1 n minus 1 factorial plus nc2 n minus 2 factorial and so on, and then we have the required formula. Now we look at the bijection principle. If P is equal to A1, A2 through n and Q is equal to B1, B2, B3, n, then function with domain P and range Q is an injective function, then n less than or equal to m. If P is domain and Q is the range, then this function is a surjective function if n greater than or equal to m. If P and Q are such that it is both injective and surjective, then f is known as a bijective function. For a bijective function, n is equal to m. Occupancy problems. The problems related to distribution of balls into boxes are called occupancy problems, and we have following cases. The first case is distinguishable ball and distinguishable boxes. Number of ways to divide n non-identical balls in r different boxes such that each box gets 0 or more balls is r to the power n. So it means that empty boxes are allowed. If no box is empty, then the number is found by inclusion exclusion principle or by recurrence relation or by generating function method. Using any one of them, number of ways to divide non-identical balls in r different boxes such that each box gets at least one object can be found, which will be equal to r to the power n minus rc1, r minus 1 to the power n, rc2, r minus 2 to the power n, so on. Now the second case is identical balls and distinguishable boxes. If an empty box is allowed, then the number of distribution is n plus r minus 1 c r minus 1. So in this case, we let x1, x2 through xr be the number of objects given to boxes or groups 1, 2 through r respectively. So x1, x2, x1 plus x2 plus through xr would be m. As each group can 0 or more, we have 0 less than equal to xi less than equal to m. That is where I is equal to 1, 2, 3 through r. We observe that the number of integral solutions of the above equation is equal to the number of ways of distributing identical objects among R groups such that each gets 0 or more. So n plus r minus 1 Cn is equal to n plus r minus 1 C r minus 1. If no box is allowed to remain empty, then the number of ways become n minus 1 C r minus 1. Now the third case is distinguishable balls and identical boxes. We mark the balls by n natural numbers 1, 2 through n. A partition of 1, 2 through n in R parts is a set of R non-empty subsets A1, A2 through AR of 1 to n such that A1 union A2 union AR is equal to 1 to 3 and through n, and any of the two sets A1, A2 through AR are disjoint. That is, their intersections are empty sets. We denote the number of partitions by S and R, which is called the Stirling number of the second kind. We can easily verify that Sn minus 1 is equal to 1, Sn comma n is equal to 1, Sn comma r is equal to 0 if r greater than n. Now I will find S and R for 1 less than r less than n. First possibility is that the number n is by itself a partition, which implies that the number 1, 2 through n minus 1 must form R minus 1 partition. The number of such partition is Sn minus 1 R minus 1. Special case is that the number n is along with at least one of 1, 2 through n minus 1 in a partition, which implies that the numbers 1, 2 through n minus 1 must form a R partition and n must be inserted in any one of the R subsets. So n can be put in R ways. Number of such partition is R S n minus 1 R. So we have S and R is equal to Sn minus 1 R minus 1 plus Rs n minus 1 R, which implies that Sn comma 2 is equal to 2n to the power n minus 1 minus 1. So this is the recurrence relation which you need to solve. And then in general, we easily find that S and R is equal to 1 by R factorial into R minus R to the power n minus RC1 into R minus 1 to the power n and so on. The final case is identical balls and identical boxes. So in this case, we find the distribution of n identical balls in R identical boxes so that no box remains empty. The number of distributions is equal to the number of ways of writing n as sum of x plus x2 through xr, where xi belongs to the set of positive numbers. R is equal to number of partitions of n in R parts. This is the same as finding number of integral solutions x1 plus x2 through xr is equal to n, where 1 is less than equal to x1 less than equal to x2 through less than equal to xr, which is equal to the quotient of x to the power n in x to the power r by 1 minus x into 1 minus x squared through 1 minus x to the power r. We denote this by PR of n. See that P1 of n is equal to Pn of n is equal to 1. P2 of n is equal to ceiling of n by 2. Prn is equal to 0 if r is greater than n. Now I'll find that Prn, where 1 less than r less than n, we divide all partition in two types. At least one partition of size 1, no partition of size 1. Again, there is a typical mistake of there is no space between, no partition. So we get that Prn is equal to Pr minus 1 of n minus 1 by Pr of n minus r, where 1 less than r less than equal to ceiling a floor of n by 2. Now we come to the last part, that is Dirichlet drawer principle or pigeonhole principle. The simplest form of pigeonhole principle is the following quite obvious statement. If n plus 1 objects are distributed into n boxes, then at least one box contains 2 or more of the objects. We will prove this by contradiction. If each box contains at most one object, then the total number of objects is n. Since we have n plus 1 objects for distribution, some box will certainly contain at least 2 of the object. Now the strong form of pigeonhole principle is given here. Let x1, x2 through xn belongs to a set of positive numbers. If x1, x2 through xn is equal to n minus n plus 1, there should be n plus 1. Sorry, there should be an equal sign. The objects are distributed into n boxes, then at least one of the ith box contains at least xi objects. This looks like there's a minus here. Okay, let's assume that's minus. Suppose that we have x1 plus x2 through xn minus n plus 1 objects among n boxes. Let ith box contain xi minus 1 objects, then the total would be sigma of xi. The I should be suffix minus 1, which is equal to x1 plus x2 through xn minus n objects, and hence at least one of the ith box will contain at least xi objects. So with this, we come to the end of theory, and if anything is not clear to you, you can go ahead and watch previous videos, and if it is not clear, it will be a problem while solving problems. Okay, so I request you to reread the theory if you don't understand, or rewatch the videos because while solving problems, we'll use these formulas. So I will end this video here, and I'll see you tomorrow in the next video, which will have 10 problems from this chapter. So in case if you want to know how many chapters are how many problems are there, let's quickly look at how many problems are there. 526 problems only. Okay. So you'll have quite a bit of practice in this chapter. So thanks a lot for watching the video. I'll see you tomorrow in the next video. Enjoy.